In the last lecture, we talked about membranes and we developed some mathematical tools to describe them as surfaces in three-dimensional space. And we introduced the Helfrich free energy to describe the energy of a membrane configuration, which turns out to depend on its curvature, much like the configurational energy of a polymer depends on its local curvature. Of course, there are differences between membranes and polymers. Polymers are one-dimensional structures, membranes are two-dimensional, so we now have two principal curvatures, or rather two invariants of the curvature tensor, for which we chose not the principal curvatures, which are the eigenvalues, but the mean curvature and the Gaussian curvature, which are the trace and the determinant. Also, and this is more of a physics thing, a polymer is an elastic beam in space. It has an entropy and an energy. The energy comes from the bending, the entropy comes from the number of configurations. For the membrane, there is the elastic properties due to bending, but there is also the fluid properties due to the lateral translations within the membrane, because the membrane is made of lipid molecules. Therefore, in the Helfrich energy, we have a curvature term, but we also had this surface tension times area, which is like the pressure times volume for a fluid term. Surface tension just being minus the 2D pressure of the system. So we can consider the Helfrich energy, or the Helfrich energy, consisting of two parts: a pure solid elastic deformation part with the curvature, and either a fluid part or specifically a liquid part which fixes the area. Or we could say, well, this is more an entropic part where we consider the surface tension versus the fluctuations of the area that are in there. Which of the two interpretations you take, with fixed area or fixed surface tension, depends on the problem that you are dealing with, and this can be a rather subtle point. Today we will do some more examples of membranes. Already in the previous lecture, we looked at spherical and cylindrical examples, two very common examples, of course, in theoretical physics because they are easy shapes. Today, we will look at a slightly more general example of a membrane that is relatively smooth and relatively flat, but still fluctuates. And we will study actually membrane fluctuations, membrane areas, and other polymer-like membrane properties. Just to make the point, for the polymers, in the end, we had a worm-like chain model where we had the energy, and then we put that back into a partition function. For membranes, in principle, we should do the same. What we should do is we should write the partition function of the membrane, so summing over all possible configurations and then weighing each configuration by its Helfrich energy. And that gives us a partition function, and from that partition function we could then get a free energy that would then give us the ultimate properties of the membrane. In practice, as we will also see today, the fluctuations of the membrane, even though they are present, are not extremely big, and therefore the equilibrium shape will be very close to the shape that actually minimizes the energy. And in practice, to find membrane shapes, we will simply be minimizing the Helfrich energy. We do get fluctuations, and we will actually today calculate the fluctuation spectrum. In order to do that, we are going to use a specific choice of coordinates, a parametrization of the membrane, which applies in principle pretty generically, but then we will make at some point an assumption that the deviations from flat are fairly small. And this representation is essentially the thing that you get if you start with a flat membrane, like a sheet of paper, and you crumple it up a little bit. But you can say, well, for every point on the paper, I can just take the flat shape as the reference and then say how high I am above the reference shape. Of course, we could also have started with a cylindrical or with a spherical shape. The principle is much the same, just the equations become slightly more involved. For cylindrical shapes, this works very well. For spherical shapes, you run into some kind of trouble at some point because the spherical shape is already curved, and therefore your equations will become nonlinear. However, for the flat shape, what we can then do is say, okay, we take the xy flat plane as our reference plane. If I say try my best drawing skills, that would be this plane. And then we have some position of the membrane in the z direction above every position on the plane. So if I were to sketch a membrane somewhere in 3D, right, for every point on the membrane, I can parameterize it by saying, okay, I have this point in XY space, and then there's some point here above the XY reference plane where my membrane now is. Right? If it's perfectly flat, then this height is everywhere the same. If it's not perfectly flat, because for instance it is fluctuating, then this height will differ depending on where I am in X and Y. Right? So then the embedding with the vector R that gives me every point on the membrane will be a function of parameters which are now simply X and Y. And these will be, well, in the X direction, I'm at X. In the Y direction, I'm at Y, and in the Z direction, I'm at U of X and Z, right, where U is then this height function. All right, so I have a position vector, and from this position vector, as we did in an abstract sense in the previous lecture, we can calculate all the properties. In particular, we can calculate the curvature. We will also need to calculate the area element when we are integrating the curvature over the whole area of the membrane. The area element is not simply dx times dy, because it's of course an area element in the membrane itself over here, and not on the reference plane, which would be down there. Right, so that one, the lower one in the reference plane, is simply, of course, the area is dx times dy, but in the curved membrane, if I have a curved surface here, if I start with this thing, if I have now a curvature, of course I need a correction vector for this area. So we'll also need to calculate that. Fortunately, we know how to do that. That's just a metric that's going to give us this extra area element. All right, first order of business is to calculate what the metric is. And for the metric, we need the induced, right? So the induced metric, so we also need the induced basis or the coordinate basis. And we found those as the two tangent vectors to the surface. And so we have an EX and an EY, which was simply the derivative of this embedding function with respect to the X coordinate, which we can now immediately write down as 1, 0, and I'm going to write derivatives of U with a little subscript for easy notation. And of course then for Y, we have the same thing, except that now we are going to get derivatives to Y, so we have 0, 1, uy. And then the metric had elements that were the dot products of these numbers, or of these vectors. Right? So we have an xx component of the metric, which is the dot product of ex with itself. So this gives me 1 plus ux squared, and yy, which unsurprisingly looks exactly the same. But we also have a cross, right, an off-diagonal term, because the dot product of the two basis vectors is not 0. And so we have ux, uy. We can put these into a matrix form, but remember, right, this is really a tensor. It is not exactly the same as the matrix. Right? So putting them in the matrix form is sometimes helpful, but can also be deceiving. Because of the curved nature of the coordinate system that we have now. From these, of course, we can also construct a normal vector, and we can calculate the determinant of the matrix, of the metric, to get the area element. Right? So what we get is, for the normal vector, it's the cross product of ex and ey. And if we calculate what that is, right, so the normal here is the cross product ex, cross product ey, divided by the length of that thing, which is also the square root of the determinant of the metric. So if we do that, then we get a full expression, which is 1 over the square root of 1 plus ux square plus uy square times, well, the cross products. So ex cross ey, the first term is going to be 0 times uy minus 1 times ux, so that's minus ux. 0 times ux minus 1 times uy is minus uy. And then we have 1 minus, and now we have an extended term, a half ux square plus uy square. All right, so we have a normal. Now this normal vector is a rather complicated nonlinear expression, and at some point we will linearize it, meaning that we will look at an expansion in terms of the magnitude of u and its derivatives, and keep only terms up to a certain order. Right, up to this point, this description is still very generic, right? The only thing that is not allowed is that you have the membrane fold over itself, because then the height function is not defined. But I can have a very large value of u somewhere and very small values of u somewhere else. This is still the correct normal vector. Right? So if we want to go to the curvature, of course we need the curvature tensor. And the curvature tensor, the elements of it were the derivatives of the tangent vector dot product with the normal, or given that the tangent vectors are derivative of the positions, it's the second derivative of the positions. So let's first calculate those. Right, so we have the xx component of the curvature tensor, that was the x derivative of ex dot product with the normal. So the x derivative of ex, well, if I look at ex itself, it only has a non-zero component in for its z variable. That's the u double x dot product with the normal. That means that I'm only going to pick up the last term. Right? So this is going to be a rather nasty expression. Right? So we have uxx from the derivative, and then we have the normal part here, 1 minus a half divided by this square root. For the yy component of the curvature tensor, of course, we're going to get something very similar, because we're now going to take the y derivative of ey, which again, right, it gives us 0, 0, and now the second derivative of u, but then with respect to y. So it's exactly the same thing, except for one thing, that instead of uxx, we have uyy. And finally, there are also going to be, well, are there going to be off-diagonal components? Well, if we take the y derivative of ex or the x derivative of ey, we should get the same thing, but both are the second derivative of the embedding function r, once with respect to x and once with respect to y. And indeed, we get a non-zero contribution, because we get the mixed second derivative of the embedding u. And other than that, again, it's the same thing. So there's two of them, so we get uxy, and then everything else is the same. Now, for the mean curvature, we found it by taking the trace of this tensor, but I told you that taking the trace of the tensor, we need to correct for the fact that we are in a different coordinate system, and the way to do that was by looking at the trace, right, by contracting, if you will, by summing over these elements, right? And the elements of the G with the upper indices that was the matrix, of which the inverse is the metric. And so we need to invert the metric tensor to get this matrix. Now I hope you all remember how to invert a 2x2 matrix. Right? So if I do write Gij as if it were a ordinary matrix, right? I have 1 plus ux squared, ux uy, 1 plus uy squared. And the determinant of this thing was what we have already seen in the denominator of the normal. Right? It's the product of the two diagonal minus the product of the two off-diagonal elements, and we see that fortunately the ux squared, uy squared terms drops out, and so we have 1 plus ux squared plus uy squared. And so if we want to invert this thing, well, inverting a symmetric 2x2 matrix, we know how to do, right? That is 1 over the determinant of this thing, And then we need to swap the diagonal elements. And give a minus sign to the off-diagonal ones. All right, so in this way, right, the product of Gij with the upper indices and Eij with the lower indices will indeed give us the identity matrix. And so if we were to treat this as a matrix, then we're now in business. But really, right, we can just read off here what the XX, YY, and XY elements are and contract those with the XX, YY, and XY components of the curvature tensor, and then calculate what the mean curvature is. And if we do that, we get, again, a very nasty expression, but fortunately, we can simplify it quite easily. So let me write out what we get. So if we do this, we get 3 terms in the numerator, and we get this square root times the determinant, which is just the square root squared, again in the denominator. So what we have is 1 plus uy squared times uxx, right? So from this one times that one, plus 1 plus ux squared uyy minus 2 times ux uy times uxy divided by 1 plus ux squared plus uy squared to the 3/2, and then multiplied in every term with the term that comes in the curvature tensor, 1 minus 1/2 ux squared plus uy squared. Yeah. So this is again still generic. It is quite horrendous because it has quite high powers of the actual function u. And so what we want to do is to say expand this in powers of u, and then at some point terminate the expansion. And so if you do this, you find that well, there are no terms that are independent of u, which is good, because otherwise we would have a spontaneous curvature here. But then there are 2 terms that are only linear in u and its derivatives, and those 2 terms are the ones that we get from the 1 times uxx and the 1 times uyy. And then there are no quadratic terms, and the next order terms are cubic. And so we're going to drop those. And so what we're left with is 1/2 times uxx plus uyy. And so perhaps unsurprisingly, what we get is that the mean curvature to second order, at least, is the average of the second derivatives. And the second derivatives, of course, are the curvatures looking in the x and in the y direction. So perhaps we could have guessed this, though, of course, there are correction terms here of order u cubed, where order u cubed means cubed not just in u, but also in all its derivatives. It's important to realize that we're making an assumption here not just on the height of the function, but also on the steepness of its derivatives. If the curvature is super high, right? If we would go to a, say, almost step function like shape, this would no longer hold, because even though the step itself may be low, clearly the derivative here at the step is extremely high. But as long as things, say, oscillate or undulate relatively, with relatively low changes and low second derivatives, then this will hold. Now you can do the same thing for the area element. So if I say, well, the total area element, that's the square root of the determinant of the metric times the reference area element, which is just dx dy. So we know what the determinant of the metric is, and then we can expand that one too. To linear, so to 0th order, that's just 1, which is what we would expect. Right here, it should have a term that's independent of u. If u is always 0, then we still have a finite area. There's no linear term, but there is a quadratic term. And so if we expand this, what we're going to get is 1 plus a half ux squared plus uy squared, plus higher order terms, dx, dy, right, plus order u cubed. This we can plug back into the energy. Before we do that, it is nice to note that we can write this still in terms of gradients and Laplacians. If I look at this thing, this is simply the Laplacian of u in the two dimensions x and y. So the notation that we're going to use for this is that this is the Laplacian, right? So the nabla squared, but then with this little perpendicular symbol below of u, right? That's this red thing. And for this one here, we have the gradient. It's the norm of the gradient of u. Right? Sorry, the norm, the length of the gradient of u, but again, the gradient in two dimensions. Right, so the gradient, of course, is the vector that's the derivative of u to x and the derivative of u to y. And if I take the norm of this thing, it's the derivative of u to x squared plus the derivative of u to y squared, which is exactly this number. And so we can write them in this term, in this form, and then use that to calculate what the energy then is. And if I plug this into the energy of a, say, finite patch of membrane, what I get, well, remember that the energy was given by kappa over 2 times the mean curvature, and the 2 is for historical reasons, and also the half is for historical reasons, though the half is fairly consistent with the polymers and even with the regular energy of a spring. And then we had a surface tension, and then of course we also had a Gaussian curvature term, but that one was a constant, so we're not going to care about it. Integrated over the whole surface. Right? And so if my surface is now a patch of, say, length L squared, so then we get that this is the integral over L times L patch, and now we're integrating over x and y, right? So this is really a square in the reference coordinate system, and then we have kappa over 2, and then so the half is killed by the 2, so we have the Laplacian of u squared, and I see I have one more parentheses, plus sigma, and then for the area element we had 1 plus a half gradient of u squared dx dy. So what does this give us? Well, for the curvature term already has a term that's quadratic in u, so we're going to combine it with this one. That's going to give us a term that's quadratic in u. If we would combine it with the second one, with this term here, we would have a term that's this fourth order in u. Well, we could keep those terms, but then we should not have dropped terms that are cubic in u from the mean curvature. So we're going to leave that one out as a higher order term. For the surface tension term, this one is, of course, a constant. So we're going to, if we combine it with the 1, then we're simply adding a constant to the energy. Constants in the energy don't matter, so we can leave that one out. And so then the relevant term will be the combination of the surface tension with this second term. And now we note that we have a half for the kappa. We also then get a half for the sigma, so we can pull the half out. And so what we get is a half times the integral. So this equals, of course, is, well, leaving out the constant term and leaving out the higher order term. So we should be a little bit careful. The patch of size L times L, kappa times the second, right, the Laplacian squared plus sigma times the gradient squared. And now we're simply integrating over x and y. And notice that this is really two different things, right? This is the Laplacian squared, so that itself is already a number. The gradient is still a vector, right? The square of the gradient is taking the norm of the vector here. So this is the energy of the membrane in the Monge gauge. And what we will do with it is to we can use this, well, for starters, we can use it to calculate energies of the various shapes, and we will get to do some of that in the problems. But what we will do with it in the next part is calculate what the fluctuation spectrum of the membrane is. We'll also then look at the persistence length of the membrane and the actual projected area of the membrane versus its real area. And in the next lecture, we will use this thing also to study what's known as membrane-mediated interactions between proteins in the membrane that are mediated by the fact that the membrane has a finite curvature.